Thank the organizers for organizing, first of all, this trimester, and also the organizers of the workshop, and for inviting me. It's always somewhat intimidating to talk in this room, but I will try my best. So I'd like to actually give some connections, really, between three different areas that seem has motivated me and other people to look at problems, and some of which are still quite open. To begin with, there's the real algebraic geometry. Okay. And then there's incidence combinatorics, which is one of the big themes of this conference. And model theory, for which for me would mean really O minimality. And I'd like to describe some old and new results which seem to go between these three areas. So I'll call them 1, 2, and 3. Might be the new one would be in this direction, and I don't know how much of that I'll be able to talk about. But let's start with 1. So Miyashari on Tuesday gave a great introduction to these algebraic methods in incidence problems, in particular the polynomial partitioning. But I'd like to point out that if you want to, so might be I just remind you what polynomial partitioning does. So if you have a finite set of endpoints in Rk, then and some number between 1 and n, let's say R, then there exists polynomial partitioning theorem of Guth and Katz says that there exists a polynomial of degree R raised to 1 over k, the dimension of the space, such that the number of points in each connected component of the complement of this hypersurface is bounded by n over R. It does not say much, in fact nothing, about the number of points that lie on the hypersurface. So it could be all the points are lying on the hypersurface, in which case you are very unlucky. But in order to use this theorem, you need to know one other thing, which is a bound on the number of connected components of the complement of a hypersurface defined by a polynomial of degree d. More precisely, you would like to know that if I have a polynomial p in k variables with real coefficients of degree at most d, then you want to know a bound on the number of connected components, so which I'll call the 0th Betti number of the complement of this polynomial. And this number is bounded by a quantity which is more precisely something like this. And this result goes back to the work of Olenek and Petrovsky from the 40s, and sometimes it's also ascribed to Tom and Milner. So I'll call this bound OPTM. Now, in fact, this OPTM, Olenek, Petrovsky, Tom, Milner, proves something more general. So if I give you any finite set of polynomials in k variables, of degree at most d, then one good thing about real algebraic geometry as opposed to complex geometry is that any affine algebraic variety can in fact be defined by one polynomial, by taking the sum of squares of the given polynomial. And in fact, OPTM proved that if I, in fact, take the sum of the Betti numbers, where by Betti numbers I mean the ranks of the singular homology groups of these algebraic variety. So I'll call the sum as B of the zeros of this polynomial. So this is the sum of the ith Betti numbers. This is given by the same expression. And once you know, for example, a bound on the highest, the k minus 1th Betti number of the variety itself, the hypersurface itself, then this follows by Alexander duality. They bound on the number of connected components of the complement. Just because it will motivate the next thing I'm going to say, let me give you a short idea of the proof of this bound on the sum of the Betti numbers. So as I said, in order to look at the common zeros of P1 to Ps, I might as well look at the zeros of their sum of squares. And the degree of this sum of squares is at most 2D. And just to simplify the ideas, let's assume that this variety here is bounded. Let's assume that but it could be very singular, right? In fact, if you take the sum of squares of polynomials, whatever you get could be very singular. So maybe it's something singular. But here, there's another good thing about real algebraic geometry is that if you have a singular variety like this, topologically you can very easily replace it without changing the homotopy type by something that's more or less non-singular. Namely, you can just replace, since this is non-negative polynomial, I can replace this by the semi-algebraic set now, which is kind of a tube around the variety. And here epsilon is small enough, so you can even think of it in this model theory conference as an infinitesimal. So we get a tube but this tube, let's call it T epsilon, the boundary of it is the 0 of this polynomial and is smooth. And moreover, the tube is homotopy equivalent for small enough epsilon to z of p that we want to control. And at this point, instead of bounding the tube, we can bound the Betti numbers of its boundary, and we can, again by an Alexander duality type argument, the sum of the Betti numbers of the tube would be at most 1/2 the sum of the Betti numbers of the boundary. So that's z of p tilde. And in order to bound now the Betti number of z of p tilde, we use Morse theory. So if you take a generic linear function would be Morse on this hypersurface, and you count the number of critical points. So assuming after a change of coordinates might be the x1 coordinate is a Morse function. So you want to know, so this number, is at most the number of solutions of the system if I take the x1 as my Morse function, and you have to know that this system is non-degenerate system, and we can bound the number of solutions by Basu bound. And Basu bound tells us that the number of critical points is the product of the degrees of these polynomials. So that's 2 times d times 2 times d minus 1 raised to k minus 1. If you take 1/2 of that, you get the Tom Milner bound on the variety. So this is, of course, old story. If this was all there to it, then it would not, I would not mention it for the incidence problem. However, to apply polynomial partitioning, now let's see if I can. No. Red. So how do I? On the right. Oh, this one is on the right. Okay. And this one. So to apply polynomial partitioning, in the case when, so you have this partitioning polynomial, I'll draw it like this, and this polynomial has degree which would depend on the number of points, so of degree d, which is pretty large, and you would like to know also not just a bound on the complement, number of connected components of the complement, but if you are bounding the incidences between points and let's say algebraic curves or algebraic varieties of small degree, then you'd like to know how many connected components does another algebraic curve meets of whose degree, let's say, is d. And the situation here is that d is much, much smaller usually than big D. So you are now in a situation where you have one polynomial which has degree in k variables of degree at most small d, another polynomial of degree at most big D. Now if you look at the proof, which I cannot look at, but you can, I guess, of the Tom Milner, you have to replace the polynomial by sum of squares, and you cannot hope to get a dependence on these two different degrees if you take a sum of squares, because it will have it will replace the polynomial by polynomial of big degree. Moreover, another side of this polynomial partitioning is that as Mika explained on Tuesday, that if you have many points, you are unlucky and you have many points on this partitioning hypersurface, then you have to do something else. So you can take care of the parts that are in these different connected components having very small number of points. But for the points that lie on the hypersurface, there is a dichotomy that you need to do something else. That's one way of thinking about it, but a more naive way would be, well, if you have many points lying on the hypersurface, why not do a polynomial partitioning of those points? Of course, this would lead to another polynomial of even bigger degree, and you will recursively have the same problem, but you can try to do polynomial partitioning again. So this leads to the technique of a multi-level polynomial partitioning. And for the moment, we do not have the algebraic tools to carry this out till the end. So the best we can do is to do it like 3 times. But if this approach would succeed, then you again need a bound on the number of connected components or the topology of algebraic varieties that needs to have a refined dependence on the degrees. So you'll need so now more generally, if you have a sequence finite number of polynomials, so for I, let's say between 1 and L, k, and I'm always letting k to be the number of variables, and suppose that the degree sequence is growing, you need to know a bound on the Betti numbers of the variety defined by these polynomials. But now the bound should depend more precisely on the degrees rather than the maximum degree. And this is not actually provided by the Tom Milner Olenek-Petrovsky bound. And in fact, optimal bound for this quantity is still not known. I mean, still not proved. I'll give you the shape of what you would expect to prove, but this is still an open problem. So maybe I'll list this as my open problem 1. But I'll say something about what we can do. But before I say that, let me give you yet another motivation of looking at this problem. And this also goes back to something we have said about the use of Basu theorem. So in the complex version of Basu theorem, which all of us would know here, if you have n polynomials in n variables of degree d1 to or k polynomials in k variables of degree d1 to dk, then the number of isolated complex zeros, which might be degenerate, but count the number of isolated complex zeros, is bounded from above by the product of the degree. But this statement, this naive statement, if you replace by complex by real, is no longer true. So you can construct examples rather easily of k polynomials, real polynomials in k variables, having only k isolated real solutions whose number is bigger than the product of the degrees. So we would like to also fix this deficiency in applying this naive Basu theorem of the reals, because in incidence problems where you are using algebraic methods, often we want to use such Basu bound to bound solutions or the number of connected components and so on. So fixing, so another motivation is fixing Basu bound for reals. So I've given motivations, but let me at least state a theorem. So this is work of my student Baron and myself. It's appeared in 2016. So under this assumption that you have L polynomials of degree d1 to dl, and we are going to assume that the degrees are increasing. So I'm going to cheat a little bit and not tell you. So this is not really increasing too much, but it's something like, okay, let me just keep it like this. So we need some minimum rate of increase of these degrees. Then under this assumption, the zeroth Betti number of the number of connected components of these polynomials, zeros of these polynomials, is bounded by the quantity d1 raised to k minus k1. I've not said what these k1, k2s are. I'll say it in a moment. Where ki is the real dimension of the variety defined by the first I polynomials. And by the way, there is a constant here, which is of the form 0, 1. So up to this constant, the exponents here, which by the way add up to k, as you'd expect, and the exponent of each degree is the dimension drop that that polynomial causes when you add it to the list of the polynomials. And this is the best you can expect, because if those polynomials were in generic position, then you would have, well, the complex Betti numbers you can calculate by characteristic class computations, and that's the shape of, well, in that case, it would be d1 times d2 times dl minus 1 times dl, the highest degree, raised to the residual dimension. So I'll say a few words about the proof of this, which is follows somewhat this idea of replacing the given variety by something that's better behaved, for which you know how to control the Betti numbers. But so we have an approximation scheme that allows us to replace the problem of bounding the given variety by the problem of bounding the Betti numbers of some many, but this many is independent of the degree, which is taken care of by this term, varieties which are non-singular complex intersections. And for non-singular complex intersections in complex projective space, you can actually calculate the Betti numbers by a characteristic class computation. And then one uses Smith inequality to bound the Betti numbers of the real part. The reason why this is just a zeroth Betti number is because our approximation is not subtle enough to catch the whole topology, like what the tube in the Tom Milner proof did, but it's enough to get an upper bound on the number of connected components. The question of bounding all the Betti numbers stays, to prove a bound like that on the sum of the Betti numbers stays open. And this is a very natural question from the point of view of real algebraic geometry, and we might not have looked at it if the question didn't arise from the incidence problems and polynomial partitioning. Questions? Okay. So might be, given the amount of time, so might be I also pose another open question. So as I said, for using multi-level partitioning, you would at least need a bound like this. But in fact, because of difficulties that you get into while doing this partitioning at each level, the real bound that we would like to have, and which we do not have, so pose it as 2, is we would like to be able to bound the Betti numbers of a given variety in terms not of, or at least not completely in terms of the degrees of polynomials defining this variety, which is not intrinsic quantity, but rather in terms of the degree of the variety itself. So there is a conjecture which appears in a paper on multi-level partitioning due to myself and Sombra, again 2016. So we made this conjecture that suppose X is an irreducible variety, and suppose that and X is defined locally by polynomials of degree delta. But what this means is that X is an irreducible component of the zeros of some polynomials of degree of bounded by delta. Then is it true that the Betti numbers of X can be bounded in terms of the degree of X and delta raised to the dimension of X? we don't have any idea of how to prove this, but that's the kind of bound that would be necessary if the multi-level partitioning has to work all through to the end. Okay, so that's as much as I want to say about connection 1. So I'll leave this. Now let me say something about connection 2 in that diagram. So one consequence of the Olenek-Petrosky bound, when you have not just one polynomial but many polynomials. So suppose you have many polynomials of degree real polynomials in k variables of degree at most d, and here I'm thinking of n as large. So these, if you look at the hypersurfaces defined by these polynomials, they partition the space Rk into regions which are defined by the signs of these polynomials, right? So they are full dimensional. So these are basic, what we'll call basic semi-algebraic sets. So that's one of them. Might be each basic semi-algebraic set might have more than one connected component, but so that's one dimensional one, and so on. So one way of trying to measure the complexity of this partition would be to consider. So I'm going to write down yet another theorem here. So this was Pollack and Roa. So for each I, we can consider the sum over every sign condition. So sign condition will associate a sign 0, positive or negative to each of the polynomials in P. So it's an 0, 1, minus 1, let's say, to P. So you're summing over all possible sign condition of the ith Berry number of the realization of this sign condition. So what I mean by Bi of sigma here is that it's the Bi of the basic semi-algebraic set, which is the realization of sigma. And the realization of sigma is the set of points in Rk which takes signs such that the polynomials take sign at x corresponding to sigma. So the sign of P of x equals sigma of P for all P in the collection. And this number here is bound, so the actual bound is a little bit more precise, but I'll write it as n raised to k minus I of some constant times d raised to k. Now for I, if you take I to be 0, this gives you the number of connected components, the number of, some people call it the cells, in the partition of Rk by these polynomials. So I'll say the proof of that is really some combinatorial type argument involving the Meyer-Vietoris exact sequence. So inequality is coming from the Meyer-Vietoris sequence plus the Olenek-Petrosky bound for Berry numbers of algebraic varieties plus some perturbation tricks. But from this, we can also consider an O minimal version of this this theorem. So an O minimal version So what should an O minimal version look like? Well, if you think of these polynomials to be given by polynomials of degree something fixed, so you're looking at hypersurfaces here that comes from some fixed family of hypersurfaces. And you have many of them, and you want to bound the complexity of this arrangement in terms of the ith Betti number. So so the O minimal version, we can fix a definable family let's call it script S of definable subsets in an O minimal structure. And so then there exists some constant let's call it. And this constant is really, in the semi-algebraic case, this Olenek-Petrowski bound, if you want, such that if you are given many of these, an arrangement of these definable sets, so for all collections from this definable family, fixed definable family, then for the ith Betti, the sum now over all sigma, and now we are looking at the partition imposed by these sets. So I'll just say membership or non-membership, so it will be between 0 and 1. Of bi of sigma. I'm not going to define what bi of sigma is, because it's the obvious thing here. And that's going to be at most this constant, which just depends on the family, times n raised to k minus I. So in particular, if you take I to be 0, that means if you have n fibers of some fixed definable map or coming from some fixed definable family, then the number of pieces in which connected pieces that which decomposes Rk is bounded by n raised to k. So number of pieces. So that has to do with the VC density of such family. But let me not. However, you can ask for something more. You can ask for what's usually called a cylindrical decomposition, which is very important construction in semi-algebraic as well as O minimal geometry. But you can ask for a quantitative version of it. So there exists a definable cylindrical decomposition adapted to this arrangement A. Now, might be I should, for people who don't know what cylindrical decomposition is, I can't define it, but let me just draw a picture. So if you have this family, the cylindrical decomposition would have cylindrical cells, and they would look like that. So each cylindrical cell is a cylinder over a cylindrical cell. It has walls, and it has it's either a section cell like this, or it is a graph over another cylindrical cell in one less dimension. Yes. And adapted means that each cell is either contained in, for each SI, is either contained in the SI or is contained in the complement of the SI. adapted. So having at most this constant times n raised to that many cells. But what is more important is that in each cell is defined in a fixed definable way Well, this is not precise, but I guess let me leave it like that. On in terms of that many, that means a constant number many of the cells Si. So this number here is really the choice of out of n of those many cells at a time. So this is what I'll call a kind of quantitative distality. The fact that each cell is defined only in terms of, in a fixed way, in terms of a constant number of the given sets in the arrangement. And it implies, through standard techniques, some Ardashana for definable graphs. Of course, not very optimal. Now, this decomposition, if you insist on having a cylindrical decomposition, which is important to have for many applications, perhaps not for this, then this is, you cannot do anything better than this doubly exponential in the dimension number. But on the other hand, if you are interested, if you don't need a full cylindrical decomposition, but you just want a decomposition of Rk adapted to the family such that each set depends in a fixed definable way on some constant number of the given sets, then you can hope to do much better, but you can't do anything better than at least the number of connected components in the partition, which is n raised to k. But you could hope to get a decomposition of size n raised to k. And if you can do that,
cells, right? I mean the sets S1 to Sn?
These sets. Did I say cells? Yes. So if you can get such a partition of size n raised to k, this would in fact lead to improvement in a whole variety of, I would say, incidence problems over even over O minimal structures. So the best we can do is something called semi-cylindrical decomposition. So I don't know whether this term semi-cylindrical existed before, but in the thesis of my student Baron, he gave a semi-cylindrical decomposition. So in this decomposition, the sets are cylindrical, but the global structure is no longer cylindrical. And it has n, so I'm ignoring the constant here, might be 2k minus 1 or something, number of cells. But what's seems like a very difficult open question is to go from something like 2k to k. I should mention that when k is small, the number of dimension is small, then I think up to 4 or 5, this optimal cutting or decomposition is known, and it relates also to the work of Chernikov and Starchenko. But this the general problem of obtaining a cutting of size n raised to k is very open and seems rather difficult. But if you can do that, then it would lead to improvement in a lot of incidence questions. So in the remaining part of my time, I will talk about oops. The connection 3 in the big picture. And this is something that I've been doing recently. And there's a motivation which comes from, in fact, from incidence problem. And in the talk of Artem on the first day, I think, he mentioned this Zemerady-Trotter theorem for O-minimal structures. And there are kind of two competing proofs, which are both adaptations of the proof in the semi-algebraic case. So the work in the Galvin, Chernikov, and Starchenko, they use cuttings, while in my paper with Oritraz, we adapted the technique of crossing number inequality to the O-minimal case. But of course, there's another alternative method, which is polynomial partitioning, that is leading to this revolution. But polynomial partitioning, why not polynomial partitioning for proving incidence theorems for over definable sets? Well, polynomial partitioning as it stands does not work over arbitrary O-minimal structures. And you might ask why. After all, the polynomial partitioning is only producing a polynomial given a set of points. And so why not use it? Well, it goes back to this issue that, well, you have this polynomial of high degree, remember, produced by the polynomial partitioning theorem. But now you also need to know that if you have a definable curve, which let me draw in a different color. This is a definable curve, gamma, lambda. So this is a polynomial of degree d. And this is a definable curve that comes from some fixed definable family. Well, you would have to know a bound on the number of connected components, or at least in the case of the plane, you need to know a bound on the number of points that the curve meets this variety of degree d. If this curve is algebraic or semi-algebraic, so if your O-minimal structure was just the structure of semi-algebraic sets, then there exists constant which will depend on the definable family, such that the number of points of intersection of this curve with the variety defined by a polynomial of degree d will be bounded by c times d. I'm just restricting myself to the curve, but the same issue will happen in higher dimensions. Right? This will be true if the curve is semi-algebraic. However, if you allow definable curve, then there is bad news, because there is the construction there is a construction by Kudica, Parusinski, and if these were the only names, then I would not have to refer to this paper, but I would never be able to remember this spelling. I'm not. Can anyone? Okay. What? Gozavich. From, I guess, 1999. That says that if for an arbitrary definable curve, there is no such function. In the sense that if you give me any sequence of numbers, they can construct a definable curve in some O-minimal structure such that this number of points, as you vary polynomials of degree d, will beat your sequence at infinitely many points. So, okay, so that's the reason why you cannot use, and we do not know how to use polynomial partitioning. So I'm out of time. I have 3 minutes. Okay, so what we can though do, and this goes through the area of random algebraic geometry. So let me just introduce the name. So you could ask the question that on the average, if you have some definable curve and we cannot hope for a bound on the number of points of intersection, but if you pick a polynomial randomly. Now, when you pick a polynomial randomly, you can do it in many different ways, but at least, so there is a particular distribution which often goes by the name Koslin, and sometimes Bombieri-Weil, which has algebraic geometric significance. So it's just not something arbitrary, and which has the property that is invariant under, the measure is invariant under unitary transformations of the space of variables. So it does not prefer any point in the projective space as a zero of this polynomial. And there is a whole history of studying the expectation. For example, if you take a random polynomial in one variable of degree d, then the expected number of real roots is going to be square root of d. If you take the number n polynomials of degree d1 to dn, then the expected number of real solutions, if you pick a Koslin independently, then would be square root of the Basu number. So there is an expectation, though it does not work always, but there's an expectation of some kind of a square root law, which I would have explained a little bit more if I had time. But let me write down the theorem that in the curve case, even though we have something better, something more general for the higher dimensions, but in the curve case, if you have any fixed definable curve, then there exists a constant such that the expected number of the intersection with the zeros of a polynomial, where you pick this polynomial P Koslin distributed, which unfortunately, I mean, this distribution you can write down in various different ways. Well, it is at most C, which depends on the curve. Well, in fact, there exists a universal constant C times the length of the curve. So this quantity depends on the curve times d raised to a half. So this is even better than the deterministic bound compared to the deterministic bound in the semi-algebraic case, which would be C times D, square root law. This theorem here is joint work with Lerario and Abhinam Natarajan, who is a student at Purdue. I think I have taken up my time. Thank you.
Questions?
Yes.
Did you say something about the relation of this last result and the counterexample? So what's wrong in that example?
What's wrong in the counterexample?
I mean, if you apply this last result,
Well, this is just an average, right? So if you fix a curve, then the measure of polynomials for which this function is very bad will go to 0 with the number of as this increases. The average is much better behaved. It's not totally surprising, and the initial hope was that must be such an average behavior would be able to make polynomial partitioning useful in the O minimal situation, but it seems like you need to at least know more on the higher moments of this some kind of measure concentration. It has to be very strong, so might be it's not possible.
More questions? Right, well, let's thank